All right, so here we have problem 11. And on problem 11, we've got a lot of fun things with differential equations. Just remembering the big concept here is that if you have the position, the derivative of the position is velocity, the derivative of the velocity is acceleration, so you can also work backwards. So here we're given the acceleration, and I know that the derivative of velocity, so dv dt, is equal to acceleration. And so I can set up a differential equation, dv dt equals a, which is negative 1 plus v. This is a separable differential equation. Divide both sides by 1 plus v, multiply both sides by dt, and then integrate because you've separated your variables. The left side becomes natural log of the absolute value of 1 plus v. The right side becomes negative t plus c. We were told up here that v is greater than negative 1, so I will ignore those absolute value bars inside the natural log. Exponentiate both sides to cancel out the natural log. So I have 1 plus v equals e to the negative t. And I can write plus c, or I can drop down a constant here and just say that's a capital C. Some people like to say we had C1 and then this is a different constant, C2. That works fine as well. And then if we solve for v, we're obviously going to subtract by 1. So then the question is, how do we get the 1 plus v naught in front of it? How do we, in other words, show that C2 is equal to 1 plus v naught? Well, we were given that at t equals 0, it has initial velocity v naught. So let's plug those values in. I'll do it over here on the left side. I'm going to plug in the initial velocity of v naught, and I'm going to say that's c2 e to the negative 0, which is great because e to the 0 is 1, and then we have our constant. So we can write out our equation now. 1 plus v, our constant, 1 plus v naught, e to the negative t. Last step, subtracting 1, and we have the desired result, that v equals 1 plus v naught, e to the negative t, minus 1. Done with part 1. All right, clearing the screen so I have some space. Part B. Initially at 0, the article moves in the positive direction until it reaches its maximum displacement, then returns. Let S represent the displacement and S max its maximum displacement. Show that the time t taken to reach S max satisfies the equation e to the t equals 1 plus v0. Okay, so here's the idea. When you have a maximum displacement, the maximum displacement is where your velocity is going to equal 0. And so if we set our velocity equal to 0, 0 equals, I'm just going to use the result from part A, like that. Add 1 to both sides. Multiply both sides by e to the t. So e to the t equals 1 plus v naught. And that's what I was trying to do because it asked for me to find the time that it takes to reach the maximum, and it reaches the maximum when the velocity is 0. You can think of that two ways. It's either optimization, like taking the derivative and making it equal 0, or when something has reached its maximum and it's coming back, it's 0 when it's stopped and turning around. That's what the velocity is. Okay, then by solving an appropriate differential equation and by using the result that we just got, find an expression for S max in terms of V naught. Okay, well, I know that the derivative of S, ds dt, is equal to V. So we know that ds dt is our expression for V, like that. This is a nice differential equation because the only variable is t, so we can multiply by dt and just take the antiderivative of both sides. So the left side, the antiderivative of ds, the right side, the antiderivative of all this fun stuff, dt. So we get s equals, when you take the antiderivative of e, it stays the same except for the chain rule. So I just put a negative in front, and then the antiderivative of 1 is t, and then don't forget your plus c right there. Okay. And now what we should do is solve for the c value. And I know that at the beginning it is displacement from 0 is 0. So if I plug in t equals 0, I will have 0 equals negative 1 plus v naught e to the negative 0 minus 0 plus c. And that tells me that c is going to equal, because this is equal to 1, this is equal to 0. So c is going to equal 1 plus v naught. So now I have an expression for s. Let's write that kind of at the top. So I know that s at any time is equal to negative 1 plus v naught e to the negative t minus t plus c, which we just calculated as 1 plus v naught. Great. What do we know about the time t to reach S max? The time t to reach S max satisfies this equation right there. And so what we can do is say that S max is equal to this. And what I'm going to do is just plug that in. So my first part is e to the negative t. So that's dividing by 1 plus v naught. If I have e to the t, this implies that t is the natural log of 1 plus v naught. So minus natural log of 1 plus v naught. And then this is my constant, 1 plus v naught. And what we end up with is this cancels to be just negative 1. And then that negative 1 will cancel with my positive 1. And so my S max is going to be negative natural log 1 plus v naught plus another v naught. Okay. So I think I'm going to pause here and make a second video with the rest of this problem.